Hello, everyone. I'm Zhao from the Colorado School of Mines in the US. Today, I'm going to present our work, Projecting Robot Navigation Paths. We contribute both hardware and software for projected augmented reality, AR. So what's the motivation behind this work? You might have seen robots on the street or elsewhere, and more robots are being deployed around public places, like airports and hotels. Have you ever wondered where are they going? Some researchers have started to visualize the path plans so people can understand the robots' navigation behaviors more. One method for conveying navigation intent is through directional projections, which do not require people to constantly wear special hardware like an AR headset and allow many observers see the projection at once. If you study robots in group, team, or crowd context, it's a great fit. And this method is proven. Quite a few human subject studies show its effectiveness. However, no code base with hardware integration is readily available. This can block innovations and advancement, especially in social navigation. Although you will see our work generalizes to manipulation tasks as well. Before we continue, let's watch a video of our work. Here, the robot shows where it goes as well as the wet floor style obstacle using projections. It also shows where its destination is. So the goal of this code paper is twofold. In the paper, we detail empirical evidence of the effectiveness of directional projections and share a robot agnostic implementation. It uses the popular ROS framework, and we also use the RViz to render the navigation paths, as you can see on the right. This way, you don't have to learn and master any computer graphics libraries. In the paper, we also have detailed a sample hardware setup, the robot, how to choose and calibrate the projector, and how we solve the issues around the power. So here are the main features of the navigation path. Specifically, we use the arrows. Some of you may know that the navigation path trajectory points are not evenly spaced in ROS because there are some probabilistic algorithms are used. To solve this problem, we contributed an algorithm to evenly space them out. To show where is the destination, we use a solid circle. While you might have thought that this technique is only about directional projections, it also works for other types of visualizations. On the bottom figure, we have projected a point cloud for recognized objects and the one in green to grasp. This one uses projection mapping technique to map back to the 3D physical world. We also projected spheres for ground obstacles and the cubes for where the object will be placed into. The evaluation of those types of projection mappings are in a HRI manuscript under review. In that manuscript, we evaluated the navigation path projection, and it achieved around 94% of accuracy for inferring the location of obstacles. Final question, how do I use it? Here is how, and with a diagram on the right. First, we need to set up the hardware. A robot is needed with a power station sufficient to power a projector. Then we need to mount the off-the-shelf projector and add a ROS TF frame. For the software, we need to run a ROS node to output an evenly spaced path as a marker array. And we subscribe it in RViz through an RViz plugin called camera stream. And finally, we output the RViz camera image through HDMI to the projector. That's all. Before you check out the code, here are 3 takeaways. First, we show that projecting navigation paths is a proven way to convey navigation intent. With our code, you can buy and mount a projector and use your favorite ROS and RViz to achieve it. And you can actually project any RViz visualizations. Last, for the hardware setup, please read our 4-page paper. In that URL, it also has code and videos. I hope our code paper will help. Now I'm ready to answer any questions. Thank you for listening.